When you face two speakers together that output the same frequency, something weird happens. Here is an example of one wavelength with an amplitude of 5 decibels, which will represent the first speaker. Destructive interference occurs when the crest of one wave cancels out with the trough of another. So pretty much the 5 in this example and the negative 5 cancel out to make 0, therefore destructive interference. The lines on my phone represent the amplitude of the sound. When the lines are longer, the sound is louder, and when they're not there, they're quiet. To explain this, we need to know that the velocity of sound is 343 meters per second, and the frequency we use is 686 hertz. We can use the equation velocity equals lambda times the frequency to find the wavelength of 1/2 meters. Destructive interference doesn't always occur when the speakers point directly at each other. Here is a setup for another demo. When we move the microphone across the measuring tape at the correct distance, constructive and destructive interference will occur. Let's do an example problem using this concept. The information we're given is that the frequency is going to be 171.5 hertz, the theta is going to be 60 degrees, and the distance between the first speaker and the point will be 1/2 meters, and the wavelength is going to be 1/2 meters. The picture representation is going to be a triangle where point P is where you're recording at, the first speaker, and the second speaker. Also, I can't draw, sorry. So, distance 1 will be from first speaker to the P, distance 2 will be from the second speaker to P, the height is going to be the distance in the Y, and x1 will represent from speaker 1 to P in the X, and x2 will represent from speaker 2 to P in the X. Using basic trig functions, we can solve for x1 to be 0.25 meters, and we can solve for the height to be 0.433 meters. Now, to find distance 2, we will have to use the equation distance 2 minus distance 1 equals n times the wavelength over 2, where n equals 1, 3, 5, and so on. We know that in order to have destructive interference, a crest and a trough have to match up. In order to make them match up, we need to shift the wave an entire half of a wavelength. So, pretty much, the difference between the two distances needs to equal half of a wavelength, or a multiple of half of a wavelength. Therefore, we get the equation, the difference in distance equals n times the wavelength divided by 2, where n will represent the multiple of half a wavelength. Now, we can just plug and chug to find the second distance, and distance 2 will equal 0.75 meters. Now, in order to find x2, we can just use the Pythagorean theorem and solve for b. b will equal x2, and x2 will equal 0.612 meters. Now to find the total distance in the x, we can just add those two together and get 0.86 meters apart, and that's how far the two speakers need to be. Here is the sound clip of the two speakers pointed at a specific point.
It's important for sound engineers to know how destructive and constructive interference works so that they can have an equal distribution of sound and not have to worry about loud and soft spots.